Oh, well, a couple announcements. I've already mentioned this, and I'm going to send out the flyer, but on Tuesday at 4 o'clock in this room, Rebecca Adams is going to be speaking about, she's a graduate student reaching the end of her graduate career at Tulane. Awesome young lady. You'll love her. She's really great. And actually, UChem majors are invited to a lunch with her, I think 11:30, but I'll send you an announcement. You probably already received it. Have you received an announcement about lunch? Okay, we'll make sure you get it. I'll send one out to this class in particular. That's just for chem majors, sorry. But it's a great time to sit down with her because Rebecca, she graduated from here in chemistry, and then she said, I don't know, I want to do this whole research thing. I want to go off and be a teacher. So she went off to be a teacher, and then she went off to be and I'm sure she was a fine teacher, but she didn't really like it. And then so she went off to be in industry and just didn't really like that. So now she's really found her niche in graduate school. She loves doing research, and so she'll talk about that over lunch, like sort of what it's like to be a graduate student and the path that she's come down. But then also she's going to talk about her research here at 4 o'clock in this room on Tuesday. All right? And then I think right afterwards there's a softball game, women's softball at 5 o'clock. So if you can catch that, that'd be great. I understand they're on a tear right now. They won like 4 out of 5 games last weekend. So yeah, should be a fun game to see. All right. But Rebecca for sure, see her at 4, and I'll send y'all an announcement about that. All right. Let's see. I want to. Where are my notes? Can I close it? Sorry, give me just a second. We're going to have one more thing for electric fields, and then we're going to move into circuits. I think that you'll find circuits are, at least these first circuits that we'll be doing, are a little bit easier than what we've seen with potentials and fields and fluxes and all that business. So if you've had trouble, just know that we're shifting gears and we're moving into something new. I like circuits. I think they're a lot of fun. They're kind of like little puzzles, especially the first ones that we'll do. Later we'll get into some more complicated circuits, LR and LRC circuits and the like, AC electricity. And those are a little more math intensive, but we'll see some cool things, like we'll do some differential equations, and we'll see some different functions, some decay functions that are useful for analyzing those types of circuits, but they're also really useful for other things that you'll do where you see similar behaviors. All right, now last time we did this, and I just want to give y'all one more practice because you're very likely to see this on the test, where I give you a function for the potential, and you have to tell me what the electric field is. This is really nice because it gives you an easy way to figure out the potential, the electric field, if you have a particular potential function, either in a molecule, in the lab, something that you created artificially. And so you can calculate what is the electric field very easily. So what we did to do this is if we have a function for the potential, remember this is a scalar quantity, so there's no directions associated with this. It gives the potential as a function of position in x, y, and z coordinates. And so if you wanted to know the potential at 1, 1, 1, you would just say x equal 1, y equal 1, z equal 1, and you'd get that the potential at that point is 3 volts. 3 times 1 squared times 1 times 1. If we want to know the electric field, I take the negative of the partial derivative. So you haven't seen partial derivatives before, but they're really not that much different from just a regular derivative. Now, if you go on and you take a partial differential equations class, you'll find that they're actually a lot more complicated than that. But for our purposes, it's really just like a derivative where we're just setting the variables that we're not taking the derivative with respect to. That's a lot of words. We're setting those as constants. So in short, if I'm taking the derivative with respect to x, I just say y and z are numbers, and they just come out of the derivative. So in that way, it's just like Calc 1, what you've done in Calc 1. All right, we did some examples here. Now I want y'all to try that. Oh, and so when I get a function for the electric field, if I want to know the electric field at a particular position, I just put in the values for x, y, and z. So if it's at x equal 2, y equal 3, z equal -1, for example, you just put in those values. Let me show you an old test question. You'll probably have one very similar to this. It'll be a different function, of course, but, similar. Look at this potential function. And just tell me what is the magnitude and the direction. I don't know. Just tell me the electric field, and then we'll think about the magnitude and direction. So what is the electric field at that position, at x equal 1, y equal 1? You'll notice there is no z in this function, so your electric field will not have a z component because the voltage doesn't change in the z direction. We're going to take the derivative of this function with respect to x. Don't forget your negative. Another half minute or so, and I'll jump in there. Once you begin to see these, they get fairly routine. What's the derivative of this portion with respect to x? What, just y squared, right? This, you just treat this like a number. The derivative of x is just 1, so it's just going to be y squared. And the derivative of this with respect to x, what is it? 3y, right. And what about this? No. How does this number change with respect to x? It doesn't change, right? Because it's not dependent upon x at all. So the derivative of this is 0, right? So this first function is going to be the negative of, what do we say, y squared minus 3y plus 0. And then we can do the same for ey. Ey is going to be negative del v del y. Or that's the Greek letter delta. Well, it's sort of a funky delta. It's not really the Greek letter delta. I don't know what it is. Where does that come from? Does anybody know? I think it's just like a bastardization of the Greek letter delta or something. I don't know what it is, but it's negative del y. Probably look at this and tell the derivative more readily. What's the derivative of this little portion? It's 2xy. It's like I just take the x away and I ask, what's the derivative of y squared? And the derivative of y squared is 2y, right? The derivative of this is minus 3x. And the derivative of this is just minus 4. Right. So I have negative of 2xy minus 3x minus 4. And so that is my electric field in the x and the y direction. Yeah, Dustin? Oh, because I have a negative right here. And the derivative of y is 1.
Should that be plus 4y?
Is it plus 4y? Oh, yes. I'm sorry, I just carried it down incorrectly. Thank you. You'll follow? I just made a mistake and copied the function. All right, so this should be plus 4. All right? So now, if I want my electric field, I say the electric field is EXI plus EYJ. Now I can go back and put in my values. I have x equal 1, y equal 1. So this is going to be equal to negative of 1 squared minus 3 times 1 plus 0. So that's 1 minus 3 is, what, negative 2, so that's plus 2. And over here, similarly, I have negative 2, 1 times 1 minus 3 times 1 plus 4. So that's 6 minus 3, negative 3. So at that position, at x equal 1, y equal 1, my electric field is equal to plus 2i minus 3j. That's in newtons per coulomb. So that is my electric field. This question goes a little bit further, and it asks, what is the magnitude and direction of the force on the electron? Well, remember our force is equal to Q times E. So I would say 1.6 times 10 to the minus 19 times that vector, 2i minus 3j. And because I'm looking for this for an electron, I'm going to put a negative there, and that'll just tell me that the force that this electron feels is exactly the opposite of what a proton would feel. Now I'm not going to work through, but you could go forward and figure out what is the magnitude and direction. Use your Pythagorean theorem, use your inverse tan to find the magnitude and direction. All right? It won't be a lot of points on your test, but it'll probably be, 7.5 to 10 points. Y'all can do that? Common mistakes that students make, I wouldn't count off much for this, but they sometimes forget the negative. The negative is kind of important because it, changes the direction of the vector. And then they get the derivative wrong. They just forget how to do the derivatives or whatever. But I think y'all can do that. Right? All right. It's a pretty exciting thing because it allows you to take a scalar function and create your vector field and determine what is your vector field, which is not something that we can do always, and it's actually not that difficult to do. All right, let's move on to capacitors. And in this first section, we're going to look at capacitors sort of as devices and not so much in circuits, and then we'll move on into looking at them in circuits. You'll see that there are some comparisons, I guess, between capacitors in circuits and what you've been doing in the lab with resistors in circuits. There are also going to be some differences, unfortunately. We're going to get to resistors, and also resistors will probably be on your test coming up in a couple of weeks. But there are differences between capacitors and resistors, and I'll try to highlight those as we go along, but it's important to keep them separate in your mind, but also notice their similarities as well. Well, let's look at capacitors. Capacitors consist of two metal plates. Of area A, separated by a distance D. All right, so this is just a little cartoon version of our capacitor. You have these two metal plates. In a parallel plate capacitor, they're called that because the two plates are just parallel to one another. We'll see some other capacitors where they sort of take that parallel plate and they wind it up, kind of like a roll-up or whatever, or they wind it up, and that just makes it easier to put into a circuit. The first parallel plate capacitor was, early 1800s, I think, late 1700s maybe. They just took two metal plates and put a piece of glass in between it, and they were about this big. And they learned that you can store charges with that. And that's actually what a capacitor does. when you connect it to a battery or some other power supply, the capacitor becomes charged. And it stores electrical energy that can be used later. And we'll see that capacitors, that's really their primary purpose, is to store energy in a circuit and allow you to use it later. We'll also see that capacitors are often used in timing circuits. So when you have something that's delayed, then you can use a capacitor, like a flashing light or something along those lines. But that's the same as storing energy. You store it up, and then you use it. You store it up, and then you use it, like a flashing light. When you get charges on a capacitor, you get a plus Q over here, and then you get this induced charge that has the same negative Q on the other side. And we'll talk about that a little bit later when we get to capacitors in series. But you get these induced charges on either plate. Remember, the charges don't touch, so you never actually have a current, or rather you never actually have charges that flow between the two plates because they don't touch. In fact, if you do get a current that flows between the two plates, that's very bad. That means that your capacitor is blown, basically. And you can search YouTube and find all sorts of capacitors that are being blown up, and it's kind of cool. They just sort of explode. But you don't really want that to happen. That's not what it does. The capacitance of a capacitor is defined by the amount of charge it holds with a certain potential difference or with a certain voltage between the plates. And so that capacitance is Q over delta V. The units are the farad. Actually, hold on. I like to think of this as sort of like the Ohm's law. Often we write this expression as Q equals CV. And many of you that are in lab, you've seen Ohm's law, which says that V is equal to IR. This is sort of a relationship between the voltage and the current for resistors. And so I like to think of this as sort of the Ohm's law for capacitors that describes the relationship between the charge and the voltage for capacitors. Whereas Ohm's law describes the relationship between the voltage and the current for resistors. If you're not in lab, you haven't seen that yet. But if you are, that's sort of a similarity between the two. That this expression for capacitors, Q equals CV, is a lot like Ohm's law. And we'll use it in much the same way. It's not the same because they're different devices, but it operates sort of in the same way. The units for capacitance are the farad. After Michael Faraday, he was sort of the late 1800s, I think, early 1900s. He did a lot of the pioneering work for electricity. He's sort of the reason that we have electricity today, because he determined that if you change the electric field, then you can generate an electric current. And so it's the way that we have everything that we have today. So he's pretty important, and that's why they named this after him. The farad is equivalent to 1 coulomb per volt. Remember, we define our capacitance as Q over V, so it's a coulomb per volt. And so, for example, let's say the previous figure, we had a 12-volt battery. And so if we wanted to know the capacitance of that capacitor, we would say, well, C is equal to Q divided by V. And since we hold 24 microcoulombs with our 12 volts, then we'll have a capacitance of 2 microfarads. We'll sort of carry our units when we're using ohms, or excuse me, not ohms, when we use this expression. So for example, if I have Q equals CV, let's say that C is 2 microfarads and V is 6 volts, then that'll give us a Q of 2 microcoulombs. The SI unit for capacitance is farads. All right, but often when we're using this expression, we'll just use microfarads or nanofarads and we'll just carry the micro over. We don't actually have to change this to 2 times 10 to the minus 6. We can keep it as 2 microfarads, but then we just carry our micro over. You'll get the hang of that because we'll do it a lot. But there are a couple cases where you actually have to change the capacitance to farads, and I'll show you that. It's coming up soon. But capacitances are very small typically. Like when you have capacitors, they're going to be on the order of microfarads. And actually to have a farad capacitor is a pretty big capacitor. So this is a capacitor. This is a 4 farad capacitor operating at 24 volts. So how much charge in coulombs does this capacitor hold? It's 4 farads at 24 volts. No, not 48. 4 farads at 24 volts is 96. You say 4 times 24 is 96. So this thing holds 96 coulombs of charge. That's a lot of charge. Do you know where this came from? Do you know what it's used for? Anybody ever seen one of these? It's a capacitor. A student gave it to me. No, not a speed coach. It sort of looks like that. It's used for, you know, boom, boom, boom boxes, like in a car stereo system. I don't know exactly what it's used for. I think that maybe it's when you have like a big punch, you need a little extra energy, and that's what this is for. Am I right? Anybody do car stereos? No. Brandon crocheted in it. Anybody know Brandon? He does drift cars and stuff. He's a cool guy, right? Isn't he cool? Like he drives race cars. Isn't that cool? Anyway, he gave me this. So you can pass it around. It's a 4 farad capacitor. It's a big capacitor. Yes. Because 2 times 6 is 12, right? Thank you, Jim. Let me fix that right here. That should be a 12 right there. Yeah.
Do you have any suggestions on how to differentiate between micro and mu whenever, like, we're writing them? Since my micros and mu's look the same.
Micro is a mu. It's the Greek letter mu. Doesn't it look like a mu? Did I draw it like that? Yeah, it's the Greek letter mu. The lowercase Greek letter mu. Yeah, good question. You really need to learn the Greek alphabet.
Micro.
Coefficient of friction doesn't have units.
Right, but it has a mu in it though.
But that's the variable, not the unit. Yeah. Y'all know I can say the Greek alphabet? Have I ever told you this? Y'all want to hear the Greek alphabet? Alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, mu, psi, omicron, pi, rho, sigma, tau, upsilon, phi, chi, psi, omega. Thank you, thank you. My kids can sing it too. I took a Greek class a year ago, and I had to learn the Greek alphabet. All right, let's try this quick test, now that I've dazzled you with the Greek alphabet. Capacitor is connected across a 5-volt battery. An identical capacitor is connected across a battery of 2 volts. Which has the most charge? All right, we'll stop at, say, 45, 45. Just guess if you're not sure. Okay, let's see. Y'all sort of putting A and B. Look, if I have Q equals CV, I have the same capacitor. And so the one with the most charge is the one with the bigger voltage. So the one that is connected to the 5-volt battery has the bigger voltage. All right? If I put more voltage across an identical capacitor, I get more charge on it. You can sort of think about that because, you know, voltage is energy per charge. And if I give more energy to my charges, that means I'm going to be able to put more charges onto those 2 plates. Okay, so for a parallel plate capacitor, remember we have 2 geometric proportions. We have the separation between the plates, D, and then we also have the area of the plates. In the capacitor that I'm passing around, it has two plates, but then they sort of roll them up so that they can store them in a cylinder like that. Well, I want to ask you a question about these geometric properties. How does the amount of stored charge, that's the capacity to store charge, or the capacitance, how is the capacitance affected if the area is increased? So if I take these plates and I make them bigger, can the capacitor store more charge, less charge, or the same amount of charge? Now, I haven't told you this, and no reason why you should know it, but I think that you do know. Sort of intuitively, if I make my plates bigger, can they store more, less, or the same amount of charge? Think intuitively. I don't try to think too much into it. If I make my plates bigger, can they store more, less, or the same amount of charge? All right, looking pretty good. I'll stop at 55. Okay, that's awesome. If I make the plates bigger, I can store more charge. And I'll tell you not a funny story in just a second. Let me do this other question now, okay? How is the amount of charge affected if the separation between the plates is increased? So now I have the same plates, I keep them the same size, but I just move them farther apart. Okay? So think about how does that affect the stored charge? If I move my plates further apart, does that mean I can store more charge, less charge, or the same amount of charge? And do your best on this. If I move my plates farther apart, how does that affect the amount of stored charge? This isn't quite as intuitive as the first one. Okay, y'all doing sort of okay. Pretty good. More have it right than wrong. But I'll still give you the funny story in just a second, okay? I'm going to stop at 54. Okay, the capacitor will be able to store less charge. If I move them further apart, it'll be able to store less charge. Remember I brought the Van de Graaff generator in here? And I held the little ball up next to it, the charges jumped across. This isn't the funny story about it, I'm just trying to relate this. The charges jumped across. In order for it to jump across a long distance, I had to wait for it to store up a bunch of charge, for it to build up a lot more energy. It just requires more energy to get those charges separated by a bigger distance. That's not a perfect example, but if I separate my plates, I need more energy to put more charges on there. So if I separate my plates more, the capacitance to store charge decreases. Okay, so this isn't it's not really an event that happened, it's just sort of something I've been thinking about. It's not physics at all. And it's kind of vulgar, like it's sort of middle school thoughts, okay? So y'all are okay with that, I think. Like we did the whole bed joke, right? Y'all didn't tell anybody? Okay, good. So, guys get up in the morning and they go to the bathroom. I mean, women do it too. But we call that the John, right? The bathroom, we call it the John. You ever heard that? You gotta go to the John? I don't think people use that word much anymore. But I had an idea that instead of calling the bathroom the John, you could call it Jim. I mean, why not Jim, right? John, Jim, that's sort of the same. And then when you get up in the morning, you say, well, gotta go to the gym. And that sounds a lot cooler than saying, gotta go to the John. Don't you think? Do you agree? Because it sounds, I'm gonna go lift some big weights at the gym. But you're not really, it's just, you're going to the bathroom.
Is that how you speak in the morning?
Brandon, I do not speak in the morning for about 2 hours. Like I like to get up before everybody else, a couple hours. So my daughter usually gets up at 5, and my wife too. So I get up at 3. But the other morning I got up at 5, and this morning too because we had a star party last night. But I got up at 5, and then my daughter, she gets up, she wants to talk. And I'm like, hey now. Shut up. What was I say? Be quiet now. Stop talking. Stop talking to me. Don't talk to me. But, so I don't know what I talk like in the morning. So if C is proportional to these two variables in this way, and it is, if I increase my area, my capacitance increases. If I increase my distance or my separation, my capacitance decreases. Then we can create an expression for C that looks like this. I'll leave a little space here. I'll come back to it. But it's equal to A divided by D. And then there's a proportionality constant, which is this epsilon naught, which is the permeativity of free space. We've seen this before. Remember, it was related to K, our Coulomb's constant. So it's sort of wrapped up in the forces that charges feel. But this is our capacitance. So now we have two expressions for capacitance. We have that expression, and we have this expression. And we'll have similar things for resistors. In fact, when you did the Ohm's law lab, you've already saw that R equal rho L over A. And we'll see a similar pairing of descriptions of the resistance as we have here. One that's based on the geometric properties, and then one that's based on the voltage and the charge, or in that case, the voltage and the current. All right, let's try this quick test. Here you take a capacitor and you charge it. You take a capacitor, you plug it in, and you charge it up with a 12-volt battery, and then you take the battery off. And so now your capacitor has charge on it. But some capacitors are variable, and you can change the capacitor. So what if you took your capacitor and you said, I'm going to make my plates twice as big? What's going to happen to the voltage across your capacitor? The charge remains the same, but what happens to the voltage? Charge up my capacitor with 12 volts. That gives it a certain amount of charge. And then I'll say, now that I have that charge in there, I'm going to change the size of the capacitor, the area of the plates. And what will happen to the voltage? It's not A, I'll tell you that, because the voltage does change. But how does it change? And by the way, in a circuit, while it might be difficult to change the physical dimensions of a capacitor, you can have a circuit where you add in more capacitor, which would change the overall capacitance. So this is a nice way of varying the voltage in circuits. By the way, I understand that Dr. Wayman is starting to do advanced circuits in quanta. Is it quanta? Y'all taking quanta right now? Maybe it's instrumental that he's doing. He's doing like more advanced circuits. That's exciting. So you'll see capacitors again there, I think, or in weekend you'll see capacitors. All right, let's stop at 155. Okay, so y'all are sort of stuck between B and C. Those are good ones to be stuck in between. Well, let's look at this. I have Q equals CV, and then I have this C equal epsilon naught A over D. Now I know if I double the area of the plates, that's going to double my capacitance. And so I'm doubling my capacitance over here. But I know that the charge is remaining constant. So in order for the charge to remain constant, if I double my capacitance, I have to halve my voltage. So whereas it was 12 volts, now it has to be 6 volts. So C is right. Good job, 9 of you. You'll see sort of relationships like that, and we'll see some more questions later, but you'll see relationships like that in the multiple choice part of the test. Let's look at dielectrics. The dielectric is an insulating material. It's inserted between the two plates, and it serves two purposes. One of the purposes is that it just increases the capacitance of the capacitor. So if I have a capacitor, it has a certain C, a certain capacitance, and then I put this dielectric in between it. Usually it's like paper that's covered in wax or something along those lines. When I put that in, it just increases the capacitance. The other purpose is more pragmatic, is that it keeps the two plates separate. Because you're probably thinking, gosh, it must be difficult to keep those two plates from touching one another. Just keep them out in free space without actually touching one another. So what they do is they take two metal plates and then they insert something in between them, some wax-covered paper usually, and then you can take that and you can roll it up. Y'all been to roly-poly like they used to have here in Thibodeau? Remember that roly-poly they had at the Shell station? It predated Chubby's. Remember when Chubby's was there? Wasn't it good? It's like right down the street from my house. Y'all ever go to Chubby's? Oh, that's good. And like when it moved down the road, it was never the same. Yeah. But anyway, before that they had roly-poly. And they would take two tortillas and they'd put some meat in between them and then they'd roll it up. Actually, it's one tortilla. But imagine two tortillas with meat in between. The meat is like the dielectric. And then you roll it up. And it keeps the two plates from touching. All right. So usually paper or something similar. Oh, there's a picture of a dielectric, or rather a capacitor. This is one that's been blown up. So remember, if you put too much voltage between it, those charges will actually jump across the gap, and that causes it to explode. I think I have a little quick test question. Yeah, this is a calculation, so try this out. You'll be doing that. I want to pull up a video. I have a video I want you to watch. When you need that epsilon, it's on your equation sheet, so you can just flip to the back and find the epsilon naught. That's your permeativity in free space. I gave it to you, but it's on your equation sheet as well. That 8.85 number. About 10 more seconds, 15 seconds maybe. Stop at 235. 235. It's 5 seconds. Just guess if you're not sure. All right, so given physical dimensions of a capacitor, we can determine its capacitance. I'm pretty sure B is right, but let's double check. So we say C is equal to kappa A, excuse me, sorry, let me rewrite this. C is equal to kappa epsilon naught A over D. Remember, this kappa is the dielectric constant. In this case, my dielectric constant is 1.5. The dielectric constant, by the way, doesn't have any units at all, and is only determined experimentally. You don't calculate it in any way, although I guess you could model it. But anyway, the dielectric constant is 1.5. That epsilon naught, if you looked in the back, it's 8.85 times 10 to the minus, is it 12 or 11? 12. times the area, which is 0.4 square meters, divided by 1 times 10 to the minus 6. So, is it 5.3? Is that right? Okay. So 5.3 times 10 to the minus 6 farads. Notice it comes out in farads, but we express it in microfarads. All right, let me show you a video. A little film canister with some aluminum foil. He puts aluminum foil on the inside of the film canister and aluminum foil on the outside of the film canister. So you have two metal plates separated by insulator, the plastic cup, the little plastic cup rather. And then you can put charges onto it. If you know somebody that's doing like a science fair project, it would make a nice science fair project to explore the properties of capacitors and how changing the area or the separation between the plates will affect the charge that it can hold. There's certainly within the realm of a high school student. All right, just a couple more minutes. Let me show you the symbols that we'll use, because next time we're going to get into circuits a lot. And we're going to be in circuits basically the rest of the semester. We're going to have all different kinds of circuits that we'll look at. So let's go ahead and give you some of the symbols that we'll use. For the battery, you've seen many of these in lab, but for the battery we'll use a symbol that looks like that. That's what I'll use. Sometimes you see some variations on this. You might see the battery with like the voltage below it, or sometimes you might see the battery with the voltage below it and a plus and a minus. On a power supply, or typically the colors that we use to represent these two sides, is red on this side and black on this side. All right, we typically say that the red side is the high potential, and the black side is low potential. You know, potential energy, that is. And you'll see what I mean when we get into DC circuits, that electrons gain a bunch of energy here, and then they return here when they don't have much energy. Remember, potential is energy per charge. For capacitors, we'll use this symbol, two lines that are parallel and in the same length. Sometimes I'll put, or usually I'll put the capacitance below it. Sometimes, I won't use this in this class, but sometimes you see in diagrams a symbol that looks like this, where you have one curved line and one straight line. But I won't use that, but you might see it in other circuits. You might have seen it before, in fact. And then a third that we'll use, we'll add some more symbols later that we'll use later in the semester, but we'll also use the resistance. This will come next chapter. All right, so those are the symbols that we'll use. And I'm going to let y'all out early today.